this announcement on our Monday lecture. So a couple of things. First thing is Dr. Mackenzie Anderson will be here in my place on Friday to talk to you about like stereo center, assigning RMS stereo configuration, etc. I'll also post my version of the stereo chemistry lecture note and also the recording onto our YouTube channel probably later this weekend. And also because I'll be traveling from tomorrow and Friday, I had to cancel our Thursday office hour. So again, to amend it, I already host a Q&A session on Monday. I will again host a Q&A session around noontime after my second lecture, or just meet outside in the open area in front of the lecture hall, because I would rather stay outside at this moment. And also, if you need any help, the TA office hour are posted. You can find those information on Canvas under module. It's under our first module. There's a list of the TA office hour. And if you need any other help, you can also send them another email aside arranging new office hours. Okay. And for today, we'll spend about 10 minutes to catch up where we left over, which is talking about functional group. And then the rest of today, we'll be talking about conformation of molecules. So if you have a molecular kit, now is a good time to get it out. And we'll be using it for a majority of the time of today's lecture. And also you can play around with it after the class, after we finish talking about it. All right, see if we have any questions before we get started. Okay, and just one more thing. You're expecting to have, our first midterm exam next Wednesday. It's a nighttime midterm exam. So next Monday, we'll have a buffer lecture, basically just me going over the major topics of this past couple of weeks with you. And then Wednesday morning, in our normal class time, it's an optional Q&A session. You're welcome to come here. It's more like a huge office hour. Everybody comes in and you ask any questions you have in mind, and we work on it together in class. All right, let's get started. From where we left over in our last lecture, we talked about functional group with carbon-oxygen double bonds, or specifically we talked about aldehydes and ketones. And these two represent one very important class. It's like carbonyl compounds. And you'll learn that in 14D, these functional groups are special because they have two different types of reaction centers, right? Given the electron negativity difference between the carbon atom and the oxygen atom, you have a relatively electrophilic carbon center at that carbonyl carbon. So that's one interesting reactivity center. At the same time, the carbonyl oxygen has lone pairs available, so that oxygen can also act as a nucleophile. So by just that basic understanding of the property of the carbonyl group, you can get an idea about why these compounds can undergo different reaction mechanisms depending on their condition. We went over the arrow pushing of the acid catalyzed addition and base catalyzed addition. We find out they can undergo very different reaction mechanisms for the similar nucleophilic addition to take place. Again, what I expect you to know is not to derive and write out the entire mechanism. It's rather if I tell you what the starting material is, what your reactant is, what your intermediate is, can you use the arrow pushing to finish the reaction mechanism? And can you identify where the reaction takes place and why that is the case? Say identify where is the nucleophilic part, where is the electrophilic part in that specific functional group, in that specific molecule. All right, so that's a bit of the review. With that in hand, we have a handful more of functional group we would like to cover. Our exams are open book, open note, so you really don't want to rigidly memorize the name of these functional groups. Rather, pay a little bit more attention to what their structure is and how do we understand the chemical reactivity of these functional groups and how to quickly identify these functional groups in a complicated organic molecule. We'll see some examples together. A few more examples we can do together. As the first one is carboxylic acid. So in the carboxylic acid, judging by its name, it's acting as an acid. And the reason here is we have a very acidic hydrogen here. All right. And now let's ask a quick question. Why is this hydrogen in the carboxylic acid functional group very acidic? So this goes back to our lecture when we talk about the Bronsted acid base. Remember when we're asking why is the hydrogen acidic? What we're justifying is, are we forming a stable conjugate base? So upon deprotonation, we're forming the conjugate base of the carboxylic acid. And obviously, we can do an arrow pushing that show you the electron movement and draw the corresponding resonance structure of this conjugate base. So R stands for any alkyl group, so any carbon-hydrogen single bond species. Here your oxygen would have an anionic charge, and here is a double bond. And what we say is the conjugate base of the carboxylic acid is stabilized by resonance. Yes. Right, so the question is, how is the electron flow when we're drawing the arrow here? So if you think about it, what we have is electrons in this oxygen lone pair goes into this carbonyl carbon. And the reason that flows that way is we know this carbonyl carbon has a partial positive charge and that oxygen has a partial negative charge. So it goes to that carbon, and then the double bond, electron in the double bond moves onto that oxygen. There are also other ways of drawing it. So occasionally people also draw it from the lone pair onto the single bonds. That's just two different ways of drawing it. You're not going to be counted wrong if you point that bond to that single bond. It just, I prefer draw it onto the carbonyl carbon, that's all. So that's the carboxylic acid, right? It's a functional group. It looks like a new point of material, but in fact, its chemical property lies within topics we discussed before. Like, why is this hydrogen acidic? It's because of stabilized conjugate base, and why that conjugate base is stabilized, that's because of the resonance structure that's stabilizing it. So this is one of the points that organic chemistry is actually all connected. It's trying not to memorize everything, it's trying to understand what's going on, and that helps you mastering the materials really fast. Yes? So the question is, will the other oxygen atom have an inductive effects? And the answer is yes, but it's relatively minor comparing to the resonance stabilization. And plus, the inductive effects from the electronegative atom is working the same way in stabilizing that negative charge. All right, so that's a carboxylic acid. Moving on to another class of functional groups. So this is called anhydrides. So anhydrides, like what we did before, you can look at it and you get an idea, right? So these oxygen lone pairs, they are nucleophilic. And the carbonyl carbons are electrophilic. And the R group here just say these are alkyl groups. Just as a quick comment on why it is called anhydride. So if you think about two carboxylic acids, reacting with each other. And one of them loses a OH, the other loses a hydrogen. It ends up to form an anhydride. So this piece is just an extra information about where the name anhydride comes from. All right. Next up, we have esters. So esters has quite similar structure as carboxylic acid, but in this case, instead of a hydrogen, now we have a R group. So esters, like what we said, here you have oxygen that can act as nucleophiles. And then the carbonyl carbon can act as a electrophile. So one of the things I want to quickly clarify is when you're looking at functional groups. For example, you might say this is a carbonyl group. That's correct. But this entire thing, that's called an ester. So when you're looking at a functional group in a complicated organic molecule, you want to first look at what exactly is the part of molecule we're talking about. Is it an ester or is it a ketone? And double check that answer before you put it down. Sorry. All right. And we have two more functional groups we want to cover, and then we'll do some examples together. The next step is called amides. So amides is one of the functional groups that contains a nitrogen atom. Like the oxygen atom in the ester, the nitrogen atom in the amide also have a lone pair. And in this case, the lone pair of that nitrogen can act as a nucleophile as well. And likewise, the carbon in the amide can also act as electrophilic. So amides are also part of very important group in your amino acids and in your peptides. And we'll talk about peptides and these biomolecules later on in this quarter. We'll come back and see more amide bonds. And the last functional group we have is called nitriles. So here, nitriles is carbon-nitrogen double bonds. So in this case, we have two parts of the molecule that can act as a nucleophile. So this nitrogen lone pair and also the triple bond, both of them can act as nucleophiles. In our annotated note, I added a small note saying the nitrile, the CN group, they're a very electron withdrawing group. So they'll come back and play a role in actual chemical reactivity, but we haven't discussed electron donating group and electron withdrawing group at the moment, so I won't test you on that. All right, so here is just a quick end to all the functional group we covered. We started from the very simple alkyl group, and then we start by introducing halogen into the alkyl group, and then carbon-oxygen single bond, carbon-sulfur single bond, carbon-nitrogen single bond, etc. And then we start to have functional groups with carbon-oxygen double bond, carbon-nitrogen multiple bond, etc. So this note represents a small summary on all the functional groups you will need in order to be successful in this class and also in 14D. So let's do some practice together. It's like, how do we use this knowledge about functional group in organic chemistry? One of the typical things you need to know is how to talk to another organic chemist. So this is a molecular structure of Paxlovid. So apparently that's the medication invented by Pfizer to trying to treat COVID-19. So how do you talk to your organic chemist when you look at this molecule? So typically we would say, hey, the reaction center is at the amide, at the center amide. So you want to know what does that amide referring to. So what I expect you to know is, for example, if I give you this molecule here, can you identify all the functional group impacts of it and see how do you do it. So let's just try it together and see how many functional groups we can identify in the seemingly complicated organic molecule. So let's start from the very bottom. First of all, in here, these are the carbon-fluorine single bonds, or these are my haloalkanes. All right, so carbon-fluorine single bond, or CX bond, a carbon bonded to a halogen. Next up, we have this part. It's a CO double bond, and then the NH attached to that carbonyl carbon. So this is just what we discussed. It's an amide. Apparently, we have more than one amide group in this molecule. So this is another amide. And let's see, this is another amide. And that's also an amide group. So we have multiple amide group in this molecule. All right, what else? We have a bunch of just carbon-hydrogen single bonds. So for example, this is a alkyl group. Or be more specific, this is a tributyl group. Here you have an isopropyl group. It's also an alkyl. And here that's also an alkyl group. So everything that's just carbon and hydrogen, that's your alkyl group. And at the very end, we have a nitrile. So note that in this molecule, normally when we do the bond line formula, you do not show the hydrogen. But for example, when at this position, the drawing actually shows where the hydrogen is. So that's actually chiral centers you'll be talking about on Friday. And the reason we show it is depending on whether that hydrogen is wedged out or dashed in. That's actually a different three-dimensional geometry. But you'll see that on Friday lecture. All right. So that's, one of the practice you'll do. You'll do more of these practice in both the Canvas assignment and also on the discussion worksheet. Let's do one more of these examples together, shall we? All right, so here we go. I forgot to write down the name of the molecule, but here is what we have. Let's get started. This one is a CX bond, so hello, alkane. And then this entire thing, that's our arrow group. And then on the top, we have amine. So amine, remember that's NR3, or you can also have hydrogen. Likewise, we have another amine here. And this is also an amine. So any nitrogen that's connecting to three carbon or hydrogen atom, that is an amine functional group. We have our amide, where the general functional group has a formula. This. All right, so that's an amide group. At the end, we have our nitrile. So that's a carbon-nitrogen triple bond. And here we have multiple alkyl groups, so anything that's just carbon-hydrogen single bond, that's called an alkyl group. Like this part, that's an ethyl group. This part, that's a methyl group, etc. This group is a little bit special. I don't really require you to know, but this one is a pyridine, so this is an extra. So it's not required in this class. All right. So these are the practice problems you're expected to know. You can also expect I ask you in a different way. Hey, in this complicated molecule, first identify the functional group and tell you which one of these part of the functional group is nucleophilic, which part is electrophilic. Right, so in this case, if we look at the amide, you should be able to identify that these two are the nucleophilic part. And nucleophilic because they have lone pair that can be donated into another molecule. And you should also be able to identify the carbonyl carbon as an electrophilic part, etc. So just as a quick summary, for this part of the lecture, we went over multiple functional groups. Our goal here is first of all to get you familiar with these vocabulary in organic chemistry so you can communicate with other organic chemists and directly pinpoint to the part of the molecule you're interested in. So for example, if I look at this molecule and just say, hey, I want to look at that CF bond or look at that carbon halogen bond, you should be able to quickly identify that's the chemical bond we're talking about. And secondly, by just looking at these functional groups, you can get a brief idea about which part of this molecule is open to react with the nucleophile, which part of this molecule is open to react with the electrophile, which part of this molecule is more likely to be acidic, etc. All right, so let's see if we have questions before I move on to conformations. Yes.
Yeah, so the electrophilic parts of the molecule, is that just like a carbon with 3 bonds and one of them is a double bond?
So the quick answer is yes and no. So yes, the electrophilic carbon, so far we talked about, is mostly a carbonyl carbon, where the carbon is double bonded to an oxygen. But at the same time, it's risky to say any carbon with 3 groups around it or any sp2 carbon is electrophilic. It depends on what are the other groups that's bonded to that carbon. Right, so if we have an electron withdrawing group, if we have a more electron negative atom like oxygen or fluorine bonded to that carbon atom, that carbon is more likely to have a partial positive charge and act as an electrophile. So it really depends on what the molecule is when we're talking about it. But the carbonyl carbon, you can always remember it as a relatively electrophilic carbon. That is correct. All right. So this is the end of the functional group. You'll get more practice on our Canvas assignment. I posted a new Canvas assignment on topics of today and also on Monday on Canvas. And that's due on next Wednesday, midnight. All right, so let's switch gear and start talking about conformations. Conformation and strengths. So far, everything we did is drawing the molecule on paper. We're assuming everything is just planned on paper, nice and easy. But here is a problem in that approach. So if we look at a carbon atom, we know that carbon typically makes 4 bonds, and those 4 bonds are not in the same plane. We know that sp3 carbon adapts the tetrahedral geometry. So this is what a tetrahedral geometry looks like. Right, so these hydrogen, they're not on the same plane with each other. And we went over the wedge and dash nomenclature as the wedge is pointing towards you and the dash is going away from you. So in reality, when we're looking at molecules, they can have different conformations. So this is an example of ethane. So now imagine all the blue and red and white ball, they're all hydrogen atoms. I just use different color for you to know. And we can rotate these single bonds. And it's relatively easy to rotate the single bond. And if you have a molecular kit, you can play around with it yourself. So our goal today is first to get you introduced to what does conformation mean, and how do we draw different conformation on paper using Newman projection, and how do we understand the energy associated to these rotational behavior of the sigma bonds. We might not be able to finish everything, but that's okay. We'll catch up on our next Monday's buffer lecture. That's what buffer lecture means. So let's get started. So before we jump into conformations, a quick of the review is constitutional isomers. So what do we mean when we're talking about isomers versus conformers? So in conformational isomers, what we're saying is the connectivity in that molecule is different. The molecular formula or the number of atoms in that molecule, on the other hand, is consistent. So for example, I could ask you to write out all the constitutional isomers of some molecule with molecular formula of C4H8O. And I'm telling you, it has a CO double bond, so it can be a ketone or an aldehyde. And let's just write out the constitutional isomers here. So for the ketones, let's see how many ways we can write it. We have 4 carbon. So apparently that's one way to write it. You can, of course, move this carbonyl group to this carbon, but they are effectively the same molecule. So there is only one possible isomer for ketone with molecular formula C4H8O. Alternatively, if we're talking about aldehyde, so the aldehyde is different from ketone because now your carbonyl or the CO double bond is at the terminal of the molecule. So if we do the count 1, 2, 3, 4, we still have 4 carbon. And aldehyde, you have the hydrogen at the terminal. And note, we do write out the aldehyde hydrogen as a convention. Normally, we do not write out hydrogen atoms, but we write out the aldehyde hydrogen because it's at the terminal. That's mostly where the chemical reaction takes place. There's another possibility of the constitutional isomer. If we look at this left part of the molecule, here is a linear structure. You can imagine that has a branch structure. So that's a different constitutional isomer of aldehyde. All right, so this is a quick review. Constitutional isomers, we're talking about structures with the same molecular formula, but the connectivity can be very different. They can be of different classes of functional group, and naturally your constitutional isomers can have very different chemical reactivity. Alternatively, when we are talking about conformers, like what we said, rotation of the single bonds, like in this case we have an ethane, right? We can rotate the single bonds, and this rotation will lead to different conformations. So conformers have conformers have exactly same connectivity. What we're doing is just rotation of the single bonds. In reality, we went over thermodynamics and etc. At room temperature, your conformers usually undergo very rapid interconversion. Or for that rapid interconversion, we call it free rotation of the single bonds. All right, so room temperature supplies enough thermal energy for your single bonds to undergo free rotation. We'll look at more details about the free rotation later on. So now let's look at the first topic here. Is how do we draw these conformations using Newman projection? Because right now it's not very straightforward to see how we're going to draw this molecule on paper. So again, if you have your molecular kit, feel free to take it out. If you do not have your molecular kit, you can pay attention to the molecular kit I got here. So let's look at ethane. First thing, let's just draw it on paper. What does ethane look like if we're using the wedge dash bound line formula to draw it? Let's think about it. What do we have here? So, again, my red part and the white part, they're all, sorry, they're all just hydrogen atom of different color. So if we have it, the way to draw it is you can have the carbon-carbon bond formed first, and then you look at it. Let's put the red one and this red one on the same plane. So this is a chemical plane. We're talking about red, black, black, red. So we have something like this. And on this left carbon, we have a white hydrogen that's wedged out, it's pointing towards me, and the blue one is dashed in a different direction. So we can write that white hydrogen wedged towards me, and then the blue one dashed into a different direction. Likewise, on the right carbon, left carbon on your end. So on this carbon here, we have the blue one that's wedged towards me, and the white one is going away from me. So this is one way to draw it. You look at your molecular kit, you derive the wedge dash conformation of your molecule. But this is not very straightforward if we're talking about rotation of that chemical bond. One of the other ways to do it is doing a Newman projection. All right, so let's do that again and see what we have. So imagine you have the carbon-carbon bond. Let me just copy-paste this molecule down here. And imagining we're looking over this single carbon-carbon bond here. All right, so now instead of looking from that direction, we're looking from the top view. So we're looking through the carbon-carbon bond here. And what we have is two different circles, if you imagine. If this is the purple carbon, so that's the front carbon we have, we'll write it like this. So in the center, that's my front carbon. We don't write out the carbon. We directly write the hydrogen atoms around it. So in the center, in the middle, we have hydrogen. The blue one here is the white one, and then here is the red one. So we're talking about the blue one, the white one, and the red one on my top carbon. And what about the back carbon? The back carbon, again, is in the back, so we don't need to write out that carbon. We can likewise write out the hydrogen atoms around it. So here we have one white one, blue one, and the red one. All right, so the view in your annotated note might be different, but if you played around with the molecular kit, you can see they're the same idea. If you look at the molecule from that carbon-carbon bond, and you get a top-down view, and the way we draw it, this is called the Newman projection. Or specifically, this conformation is called a staggered conformation. So in the staggered conformation, your hydrogen atoms are relatively away from each other as far as possible. So this is the relatively more stable conformation. Right? So what about rotation? We're talking about rotation. So how will my molecule rotate if I change its conformation, if I rotate like say 60 degrees? So I'm gonna rotate the bottom one. So I'll keep the top one as it is, and I'll rotate the bottom one clockwise by about 60 degrees. So now your hydrogen are directly on top of each other. So that's after rotation of 60 degrees, and that's the structure we end up with. Likewise, we can draw the Newman projection of this conformation. What we're doing is we're rotating the bottom 3 hydrogen by 60 degrees. We're rotating the bottom group by 60 degrees. So beneath that red one, we have a white one. Beneath that white one, we have a blue one. Beneath that blue one, we have a red one. So they are actually directly below it, just the way we draw it a little bit aside of your top molecule. And note when you're drawing it, you want to make sure you're always having it either on the left-hand side or the right-hand side, but keep it consistent. Like you don't want to have the red one here, which is not right. So keep it consistent. It can be either left or right, both are correct, but keep it consistent. So this is what happened when we rotate bottom carbon by 60 degrees clockwise. And apparently now, because your hydrogen atoms are directly on top of each other, what they will have is they will have some steric repulsion between each other and causing this conformation to be less stable. So this is called an eclipsed conformation. So eclipse means your hydrogen on the top and the hydrogen on the bottom, they're eclipsed with each other. So this is a less stable conformation. Or to be more specific, we have about a 2.9 kcal per mole torsional strain. In the eclipse conformation. Right, so that's how to draw the Newman projection. Apparently, this is why I want to emphasize. You need a molecular kit. You don't need all the molecule or all the chemical bond in that molecular kit, but having a model around in front of you will be very helpful in drawing that Newman projection. You can also use your molecular kit in our exams, so feel free to get one. You can buy it secondhand, share it with a friend. You don't need everything in that molecular kit, but having one is very useful to understand the conformations of a molecule. All right? Yes. So torsion strand, that's just the actual terminology we use to describe what is the strand, what caused the eclipse conformation to be less stable comparing to the staggered conformation. So that's the official name of that strand. Sorry. All right. So let's look at one more topic. We have about 10 minutes left, so we'll just look very carefully of ethane, and then we'll stop after that. So what we're gonna do is called a conformational diagram of ethane rotation. So we'll keep our Newman projection here. I think that's the way I draw it. All right, so that's the way you show it. And that is the Newman projection of this molecule here. This is a potential energy diagram. So it looks very complicated, but it's okay, let's just work on it one by one. When you're looking at any scientific drawing or any diagram in science, first thing you ask is what is in this diagram? What is the x-axis? What is the y-axis? So my y-axis here, that's the energy, or that's the torsional strand we're talking about. On the x-axis, on the other hand, that's the torsional angle. So we're manually defined, this is our starting point. That's our 0 degree. And then from this 0 degree, we'll start rotating one of the carbon atom every time by 60 degrees, all the way to 360. And what this diagram is reflecting is how is your torsion energy change when you rotate that chemical bond every 60 degrees. So I already draw the picture up for you, and let's walk it through. And eventually you'll get an idea in how to create these sketches on yourself. All right, getting started, this is where we begin. This is the Newman projection of the staggered conformation. And like what we said, in the staggered conformation, your hydrogen atoms are away from each other, so that is our most stable conformation. Or we can manually define this torsion energy to be 0 at this staggered conformation. And then what is going to happen? Now what we're doing is we're rotating one of the chemical bonds by 60 degrees. So let's rotate it this way. Okay, this way. So now I'm rotating it in a counterclockwise by 60 degrees. It doesn't matter which way you rotate it, it's the same idea. So now after rotated by 60 degrees, what we have is your hydrogen atom is now eclipsed over each other to form the less stable eclipse conformation. Or in this case, this point will have a higher torsion energy or torsional strand of 2.9 kilocalorie per mole. And now if you think about this torsional strand, so that's the barrier, or that's the energy barrier required for that single bond rotation to take place. So that's related to thermodynamics, and we have equations to connect that torsional energy to the relative rate of that rotation. We're not doing that calculation right now, but you should be able to do it, connecting the energy barrier here to the rate of rotation, and get an idea about why we say there's free rotation of sigma bond at room temperature. And likewise, we can keep rotating our chemical bonds. Let's do it this way. Let's see. All right. And this way we put it back into our staggered conformation again by rotating it another 60 degrees. So this is where we end up with. And again, whenever you draw it, that's showing your hydrogen atoms are away from each other. It's a staggered, more stable conformation. You can keep rotating it. And let's see, the next step we're doing it. Now we have this one. So here the red one is below the white one. The white one is below the blue one, and the blue one is below the red one, and you come back to that eclipse conformation. So it's always keep going like that. In reality, under room temperature, the ethane chemical bond can free rotate, means any of these conformations. These are all in equilibrium with each other. It's just under rapid conversion of these stable staggered conformation. We can keep doing that. I mean, I can keep doing it until we get this conformation. Now your white one is directly anti to the other white one, the red one to the other red, the blue one to the other blue, and keep rotating it. We can finish this profile. So that's the last eclipse conformation. And then we do it one more round, and we put it back to our starting point. All right, so there's no myth here. Imagining you have your own molecular kit, what you should be able to do is by just looking at it and create this type of potential energy diagram by just looking at the molecular kit. This diagram can become more complicated when we replace one or more of the hydrogen group with other sterically bulkier chemical groups. I don't have time to go over that today, so we'll save that for our next Monday's buffer lecture to catch up on this topic. So let's see if we have questions. I have 2 more minutes for questions. Yes?
So I don't really understand what the difference between all the different static things, because they're all hydrogen.
So in this molecule, all the staggered conformations are the same. But when you're talking about other molecules, now imagine I replace one of the hydrogen with a methyl group, then it has a difference. So we'll talk about that next Monday.